Hello everyone. So welcome to week 3 of NPTEL live session on the course of Foundations of Cryptography. So let me share my screen first. Okay. So let me first discuss about the assignments which are posted on NPTEL website in the last week, that is week 3. So the first assignment question was like this: which of the following is or are true for one-way functions? So as we were discussing the last week also, uh, the given options are their randomized functions. They are used in construction of PRG. OWF can be many to one function, and the time complexity to compute the inverse of OWFs is a polynomial function of the security parameter. So looking at them one after another, OWF are of course not randomized function, they are deterministic function. And then they are used in construction of PRG, which is true. We have seen such construction of probably secured PRG by assuming the existence of OWF. And OWF, of course, can be a many to one function. As per the definition of OWF, the given some input x, computation of f of x, that is the value of if f is our one-way function, then computing f of x is an easy task. That is, there exists polynomial time algorithm to compute f of x, but given some f of x for some uniformly random x, given f of x, computing some pre-image of that fx should be a hard problem. So that's how there can be more than one pre-image of some given f of x value. Computing any one of them should suffice, but computing that thing is difficult by definition of OWF. So the last option, which is given the time complexity to compute the inverse of OWFs, is a polynomial function of the security parameter, which is not at all true by the definition of OWF. So only true options given here are that OWF are used in construction of PRG, and OWF can be many to one function. Okay. So second question was, select the incorrect options from for Trivium cipher. First option given, it is a software-oriented stream cipher, which is not true, as you have already seen in the NPTEL lecture posted. So it's clearly mentioned there that it is a hardware design of stream cipher, and the cipher uses a key as well as an initial vector. That is true. It is an asynchronous cipher. No, it is synchronous cipher. And then it uses multiple feedback shift registers in nonlinear fashion, which is true. So this is very much about information about Trivium cipher. So nothing really to explain here. So I'm proceeding to the next question. Which of the following candidates is or are necessarily secure BRMs? In all the following options, f of s of x is a secure PRF, where of course x is the input and s is the secret. So you are given that if s of x is a secure PRF, then for some x and s which belongs to this n-length binary string, and output is also in-bit string, so that is a length preserving PRF. And then you were given some other constructions, proposed constructions of PRF, and you have to tell whether these proposed constructions are also secure PRF or not, given that F is a secure PRF. So if you remember from the last week's live session, we already discussed similar kind of construction of PRF about their security analysis. So let's see one after another this also. So g is of x is given as fs of x XORed with fs of x bar. So this is of course not a secure PRF. Intuitively, if you see that if you provide two such query input to the uh, like you always think about some adversary who is trying to attack the PRF construction, that is just it is trying to distinguish the PRF output from some truly random function output. So what it will try is that it will try to see some uh, functional the PRF value against its query input of its choice, and then try to case from that which is whether it is seen or whether it is communicating with a truly random function oracle or PRF. So particularly this example, so let's actually proceed to this diagram. Here you have a verifier and you have an adversary. So what adversary can do is that in this scenario, it can try to send as query some x1, okay, and in response it will see y1, which can be either the f dash k value, that is our g actually in our question. If you see it, it was given as gs of x, right? So k or s, whatever you call it, that is the secret key, and the input is x. So in response of this query input x1, the adversary sees y1, which can be computed either as f dash k of x1, or it can be some truly random function for input x1, okay. So and then what adversary can do is that it, as next query input, it can provide x2, which is nothing but x1 bar. And what will happen with that, see that if k dash is calculated as fkx XORed with fkx x bar, fk x bar, and when you provide as query input x1 bar, then it will basically get fk of x1 bar XORed with fk of x, and of course their XORed value will be so you will get same value, right? So fk of x or fk of x bar, it will be computed for both the times, and adversary checks if y1 is equal to y2. If yes, then it returns that b dash equal to 0, which is same as saying that, okay, I am interacting with PRF, and if it returns b dash equal to 1, that means that adversary is saying that, okay, I am interacting with a truly random function, okay. So that's how it can clearly distinguish. And if we calculate the distinguishing advantage in this case is that provided b was 0, that is this verifier was actually using the PRF to generate the yi's, then of course this property y1 equal to y2 will be always satisfied. So this probability that b equal to 0, b was actually 0, and the adversary outputs b dash equal to 0, that is 1, and the probability that b was actually 1, that is yi was generated using truly random function, and then still adversary got to see y1 equal to y2, that scenario can happen in 1 over 2 to the power n probability, right? So as the output string is of n bit length, and to get y1 equal to y2, that probability is of course 1 by 2 to the power n. So distinguishing advantage in these two cases is 1 minus 1 by 2 to the power n, which is not negligible. So that's how we conclude that if k dash is not secure, or gs, as in your question here was, it was denoted as g of s. So this gs of x constructed in this way, even if it is secure, this g is not a secure here. Proceeding to the next option given. This was also discussed actually in last week live session. F of x of so the key is basically here will be fs of x. So 2 times it is applied. F is secured PRF. So let's see the scenario. Basically, this will also be a secure PRF. So this is the case here. There is verifier, there is distinguisher, and we also assume existence of some distinguisher D dash, which we already assume to have the capability of distinguishing the output of fs dash from truly random. Okay. In our case, fs dash or gs, whatever it is. So let's say it is gs actually. Fs is given as secure PRF. So we will basically show that if D dash exist with non-negligible distinguishing advantage for the proposed construction of G PRF, then there must be a distinguisher who exists with non-negligible probability to distinguish the output of Fs from to random. Okay. The game proceeds in this way. D dash provides some query input X to D, and D forwards this query input to the verifier V, and V responses for each query input coming from D in either of two methods. First method, either P is 0, it will respond with the PRF value computed on X. Otherwise, it responds with truly random function value on X. So, and D gets this Y as response from verifier, and it exactly what it does with Y is that it again tosses some coin to get uniformly randomly chosen value of B dash from either 0 or 1, and B dash is 0, then it will compute Y dash as Fy of X. So the key is now Y, whatever it got from verifier. So remember that the construction of GS of X was defined like that. So it satisfies that construction Fy of X. Otherwise, it returns Y dash equal to Y. So from the view of this distinguisher D dash, whatever communication is happening between D and D dash, that is exactly as would have the communication for a security game of PRF of this PRF G. So for each query X, it gets to see the Y dash as f of Y of X. Okay, and then we assume that it responses with some bit P double dash denoting its distinguished value of whatever it tries to guess from this communication, that whether it is communicating with a PRF or truly random function. And if it is guessing the value correctly, then D says that, okay, I was also communicating with PRF, that means capital B equal to 0, otherwise it says that capital B is 1. And you can see that the probability that D wins is exactly equal to that probability that D dash wins. So, and we already know that this game of security of this PRF F is already a secure PRF. So that's how we conclude that as the probability of distinguishing distinguishing the communication between this V and D dash, whether it is communication with PRF or TRF, that is already negligible, and that implies that this communication is also negligible. So next is GSX equal to F 1 to the power n x concatenated with Fs x. Now here, very intuitively, you can see that the first half of the output will always be fixed and publicly known for any given input x, right? So whenever any adversary is querying with some input x, it can itself compute the value of fx with key as n-bit string with all ones. So if you know the value of key k and x, the PRF itself being a public function, the value f x with key as 1 to the power n is computed easily. So whenever you see the output of gs of x, you can easily easily check the first half of the output is equal to this or not. If it is, then you can surely conclude that okay, the adversary can conclude that it is actually communicating with a PI. Otherwise, it will conclude that it is communicating with a truly random function. So this is very clearly distinguishable. And the last option that is also very similarly can be done, that the first bit of the output, if it is 1, then it can conclude that it is communicating with a PRF, PRFG. Otherwise, it concludes that it is communicating with a truly random function. Now, if the verifier is actually using the first method, that is, it is actually outputting y as PRF value on x, then the first bit will always be 1. So that probability is always 1. But in the next case, if actually the verifier was using truly random function on the input x to output y, then what happens is that with probability half, the first bit of a truly random string will be 1. So distinguishing advantage will be 1 minus half, that is half, which is of course again constant and not negligible. So we conclude the first, third, and fourth, all three construction of PRF are actually not secure, and only secure construction here is the second construction. So proceeding to the next assignment. This was also actually discussed in the last week live session. So you were basically given a symmetric key cipher pi, and which is already secure. Now you try to build some variant of that such that encryption of encryption dash km is performed as encryption k of reverse string of m. Reverse means the bit string obtained by reversing the order of bits of m. Now, whenever if you just assume that this pi dash is not COA secure, that is ciphertext only attack is possible against it. So that means that if you manage to gain some information about the distribution of underlying plain text of the ciphertext of this scheme pi dash, that means that you have some information about the distribution of reverse of m, which again implies that of course you have some information about the distribution of m. And if that is possible, then the original scheme pi is not COA secure, and by contradiction we say that pi dash is actually COA secure. And similar argument can be done for CPA security. So for in such a game, if there exists some attacker A dash which is able to distinguish the ciphertext, challenge ciphertext for the game pi dash, then it can be used by some other attacker A to distinguish the challenge ciphertext of the game in the scheme pi. So as we've already claimed that pi is a secure CPA secure scheme, so that means that the probability of winning for A dash is also must be negligible. So such A dash cannot exist, which can distinguish the ciphertext of M0 from ciphertext of M1 with non-negligible probability. Such A dash cannot exist. So pi dash is CPA secure provided pi is CPA secure. This is the last question for last week assignment. Given that, which of the following statements is or are correct? A single message CPA secure encryption scheme is also a multi-message CPA secure scheme, which is of course true. Secure PRGs can be constructed from secure PRFs and vice versa. Yes, that is true. You have already seen construction of PRG from secure PRF, right? If you remember that, if you have a secure PRF, say F, then you can actually construct a PRG from that by giving input, say giving various input to the PRF and concatenate them with each other. Like says your PRF secret is S, and if of S is a secure PRF, then you can construct PRG from that by doing fs of 1 concatenated with fs of 2 concatenated with fs of 3 and so on. So like that you can construct a PRG of expansion factor L into N, right? From n bit input block, you can get Ln size of output. So that construction we have seen, and the opposite direction is also possible. That is constructing secure PRF from secure PRC, that you will see later. Next statement given as given F is a secure PRF and S and X also binary string of length n and n minus 1 respectively. The construction fs dash x, which is described as fs of 0 concatenated with x concatenated with fs of x concatenated with 1. This is a secure PRF. If you remember from last week live lesson, this was also discussed. We will just quickly look at the scenario. So this is not secure, and we argue that thing by providing some counter example. So let's say the adversary or the distinguisher provides as query input this particular input query string x1, which is n minus 1 length 0 bits. Okay, so now what it sees in response is fk of 0 concatenated with 0 to the power n minus 1, that is 0 to the power n, and that again concatenated with fk of 0 to the power n minus 1 concatenated with 1. So that is the output it sees if it is actually interacting with PRF. And then in the next query, it provides as input x2 equal to 0 to the power n minus 2 and then one single 1. And in that case, what it sees in case of PRF output is that fk of 0 to the power n minus 1 and then one single 1 concatenated with 0 to the power n minus 2 and then 2, 1. Okay. So if you see that this part and this part are exactly same, so that's how distinguisher returns basically distinguishing bit b dash equal to 0. That is, it says that okay, I am interacting with a PRF only if these two parts are same, and otherwise it says that I am interacting with the TRF. And if you see the distinguishing advantage here, this is 1 minus 1 over 2 to the power n, which is again not negligible. So we say that this proposed construction is not secure. The last statement, a strong PRP is indistinguishable by an efficient adversary from a true random permutation, even in presence of an inverse oracle. So that is by definition of strong pseudo-random permutation, that even in presence of an inverse oracle, the pseudo-randomness of the output of PRP should retain. So that is a true statement. So the last week assignment discussion is over. So let's proceed to this week's assignment and problem solving. So first problem is given as consider the following keyed function f such that for security parameter n, the key is an n cross n Boolean matrix A and an n bit Boolean vector B. Now you define the function f with secret as a comma b, which maps some input n-bit binary string to again output an n-bit output binary string such that f of x is ax plus b, where all operations are done modulo 2. You have to show that f is not a pseudo-random function. So if you recall what is the property of a pseudo-random function is that okay, so if this Zoom meeting ends, then this in the same link again. So we were talking about this function f. So for any pseudo-random function, an adversary, if it queries with polynomially many number of query inputs and sees the corresponding PRF response, and even after that, it actually should not be able to distinguish for some unknown input x whether it is interacting with a PRF or a TRF. So that is the definition of PRF. Now, if you have to show that this particular function as defined with secret a comma b, x plus b, this is not pseudo-random. So basically, you can see first if adversary can query with input x equal to all 0, so n number of zeros. And what happens is that the PRF output becomes basically b because x is all 0. So whatever value is contained in the binary matrix A, that all becomes 0. So if you basically get b as output. So the value of secret b is already retrieved by this simple query input x. Now, next what adversary can do for retrieving the secret A is that it can query with input xi of the form first I minus. So I am talking about total n number of queries. So first query is over by which B is retrieved, and after that basically n more queries are required, and which is of course allowed in case of PRA because adversary is allowed to take polynomial amount of time and polynomial number of queries to do. So it can of course do n more queries to see the PRF output for various inputs. Now for each ith query, it can provide input x as I minus 1 number of 0, then ith bit is only 1, and then again rest of the bits are 0. So n length bit string where only ith bit is 1 and all the rest of the bits are 0. If your xi is of this format, then you can easily see while multiplying the binary matrix A with xi, you will get the result as the ith column of binary matrix A. So, and already we have retrieved B. So whenever you are seeing yi for this input xi, you basically perform yi XOR B and you get a ith column of the binary matrix A. So that's how by only doing n plus 1 number of queries, you get to retrieve the whole secret binary matrix A and the binary vector B. So that is of course not a secure PRF. Okay. Proceeding to the next question. Prove that if f is a length preserving pseudo-random function, then g of s, which is defined as fs of 1 concatenated with fs of 2 concatenated with fs of 3 and so on, and till L such input, and such construction of G is a pseudo-random generator with expansion factor L into N. So this is a simple theoretical construction for constructing PRG from PRF. Let's proceed to the construction to prove it. As you know, so we again define this kind of games between verifier, some adversary A, and some peer G distinguisher D. So if such distinguisher D exists for this PRF game, PRG game, which is able to distinguish output of G of S from some truly random generated bit string of length ln, then basically the adversary A will also be able to distinguish the output of PRF from truly random output. And as we already know that if is a secure PRF, then we will basically conclude that such a D cannot exist with non-negligible probability. To see in detail, so the verifier chooses one bit, either 0 or 1. If it is the bit B comes to be 0, then it provides for each query input xi, it provides the PRF output fs of xi, otherwise it provides the truly random functional value on input xi. And now adversary queries for various value of xi starting from 1 to L. So for all I belonging to the set 1 to L, it provides one after another the query inputs xi equal to I, and in response it gets to see yi, which can be either PRF output or TRF output. Once all the L queries are done by this adversary A, then what it does is that it computes Z as the concatenated version of all these L number of yi's. So y1 concatenated with y2 dot concatenated with yl. So all these ln length bit string is generated as Z and sent to the distinguisher D. And if you consider the view of the distinguisher D, it basically sees the form of G of S whenever B is 0. So whenever actually verifier decided to provide yi's in form of PRF, then the view of the distinguisher D is just as it would be the view of pseudorandom generator G. All L output of PRFs are concatenated with each other, and it then outputs some distinguishing bit, B dash. And also, if B were actually 1, that is yi's were generated from truly random function, then each yi being truly random, the concatenation of all these L number of yi's will also be truly random string. So the view of distinguisher D is as expected. And then we say that probability that B double dash is 0, B double dash is whatever adversary A gets the distinguishing bit B dash from distinguisher D, it just replies to the verifier the same bit as B double dash equal to B dash. The same bit it returns to the verifier to say whether it is communicating with PRF or TRF. Now, the probability that given B equal to 0, B dash was actually turned out to be 0 by the attacker A. That probability is exactly same as probability that B dash is 0 provided B equal to 0, because B double dash is nothing but B dash only. So this probability is equal to this probability, and probability that B double dash was 0 provided B was actually 1. That probability is again equal to the probability that B dash equal to 0 over the event B equal to 1. Now if you see the first probability, the F being a secure PRF is already known to be negligible. So we can conclude that this probability, the distinguishing advantage of the PRG distinguisher D is also negligible. And so we conclude that the PRGG is actually a pseudorandom generator and correct construction or secure construction of a PRG. Now, here is another question. So let f be a pseudorandom function and G be a pseudorandom generator with expansion factor L of n equal to n plus 1. So for n bit of input to the PRG outputs n plus 1 bit of output. And for each of the following encryption schemes, state whether the scheme has indistinguishable encryption in presence of an eavesdropper and whether it is CPA secure. So there are two questions asked. One is whether the proposed scheme is COA secure, or presence of eavesdropper, so that is EAB secure, or it is and whether it is CPA secure or not. Now you have been given three different scenarios. We will analyze them one after another. The first construction is that to encrypt M of length n plus 1 bit, choose some uniform R of length n and output ciphertext such that the ciphertext has two parts. First part is the R itself, and then G of R XORed with the message M. If you see, so clearly this R, although uniformly randomly chosen, it is provided as part of the ciphertext itself. So there is nothing secret really in the ciphertext, as R is given and G being a PRG whose algorithm is publicly known. Only secret or only unknown part in the view of adversary for a PRG output should be the seed. But here, as R is also provided as part of the ciphertext, so G of R can easily be computed by any eavesdropper. And then whenever it sees any random ciphertext of the form R, GR XORed with M, it takes the value R, computes GR, and then it XORs the value of GR with the second part of the ciphertext, and it gets the exact value of M easily. So very obviously this scheme is not EAP secure. Just looking at the ciphertext or eavesdropping on the communication channel, the value of the plain text can be recovered. So it is not EAP secure, and also the question of CPA security does not come to the scenario at all. Consider the next construction given. So to encrypt M, which is a n-length bit string, output the ciphertext M XORed with fk 0 to the power n. So let's analyze the second one. So see that fk of 0 to the power n is a pseudorandom string because the k is secret. So without the knowledge of key k, guessing the value of fk for input 0 to the power n cannot be guessed or cannot be distinguished from a uniformly random string of same length. So the ciphertext M XORed with fk of 0 to the power n, that almost behaves like a OTP. In OTP, what happens is that the message M is actually XORed with truly random string of same length as message. But here the string is actually pseudorandom. If f is a secure PRF, then the output of fk of 0 to the power n will also be pseudorandom, and so it almost behaves like OTP, and so we can say that it is EAB secure. So any eavesdropper who is just looking at the communication channel and seeing the ciphertext only for any unknown underlying message M, it cannot guess anything about this value of fk of 0 to the power n. So any extra information about the underlying message is not leaked. And also see that this encryption actually deterministic encryption, because for any message M, the part which is XORed with the message M is always fixed. So Being a deterministic algorithm, CPA security is never ensured in case of this proposed encryption scheme. So it is not CPA secure. And the last construction, to encrypt M, which is a 2n length bit string, you parse M as M1 concatenated with M2. So basically you divide it into two halves, and such that each of the two parts, such that each of the part has equal length, and then choose uniform R of length n and send R, M1 XORed with FKR, M2 XORed with FKR plus 1 as the ciphertext. So the ciphertext has three parts here. The first part R is actually a random choice from the space in bit binary string. And the second part, M1, the first half of the message is XORed with FK of R, and the second part of the message is then XORed with FK of R plus 1. So here, as all the three parts of the ciphertext, the first part is also random. The second part, the F being a secure PRF, FK of R is a pseudo-random string, which is stored with the first part of the message, which is denoted as M1. So this part cannot reveal anything, any extra information about the underlying plain text M1 here, and for the same reason, and also say that Fk of R and Fk of R plus 1 are not related at all, because F is a secure PRF. So by looking at the second and third part of the ciphertext, no extra information about the underlying plain text message part, M1 and M2, nothing is revealed. So it is EAV secure. Now, to comment about CPA security, the game will be something like that, and intuitively, so for any such attacker, a dash, which is able to distinguish ciphertext of M0 from ciphertext of M1 in this case, after seeing polynomially many number of message ciphertext pair in the query phase, if such an attacker exists to distinguish them with non-negligible probability, then that will actually imply the existence of such attacker A, which is actually able to break the security of the PRF F. But PRF F is already assumed to be secure, so the distinguishing advantage of A must be negligible. So ADAS is also able to break the CPA security of this crypto system with negligible probability only. Proceeding to the next question. What is the effect of a dropped ciphertext block? That is, if the transmitted ciphertext C1, C2, C3 is received as C1, C3, C4, and so on, when using CBC, OAP, and CTR modes of operation. Now, as you know, all of these are various modes of block ciphers. So you have blocks as Fk, which is nothing but pseudo-random function with secret k, and you provide inputs to these blocks in several methods, and with that various methods you get ciphertext blockchain in output feedback mode or counter modes of operation block cipher. So the question here is that if such scenario happens that you have message blocks M1, M2, M3, M4, and so on, and corresponding ciphertext block you receive as C1, C2, C3, C4 usually. But in some erroneous scenario, if the block C2 is dropped, so some block Ci can be dropped, and then what happens to the decrypted plain text basically? So is it still correct decryption of the plain text? No. So let's try to analyze the situation. In ciphertext blockchaining mode, uh, this is how you do the block cipher chain, right? So you have message blocks M1, M2, M3, M4. You have some initialization vector IV, and the first block of FK takes as input MZOR IV and output ciphertext C1. And this C1 is again chained to the next block and ZORed with next message block M2 and then provided as input to FK. Like that it goes on. Now, in some erroneous scenario, say message block C2 is dropped. So what you see is that basically chain of ciphertext C1, C3, C4, C5 and so on. And you don't know that C2 is dropped. So you consider C3 to be your C2. Now what happens is that if you try to decrypt the first ciphertext block C1, you do FK inverse of C1 XORed with the IV. And this is okay because C1 is received correctly. So you get the plain text M1 back correctly. Now what happens when you want to calculate M2? What you do is that you actually do FK inverse of C2, which in your case is now actually C3. So if you calculate FK inverse of C3 and then XOR this with C1, the previous block of ciphertext. As FK inverse of C3 is actually C2 XORed with M3. But as you received C3 in place of C2, so this certainly does not give you back the message M2. Okay. Now what happens when you want to calculate M3? You perform FK inverse of C4 and then XOR the output with C3, right? So, you XOR the output with C2, which is in your case C3. So you get basically C3 XORed with M4, and with that you XOR C3. So you get back M4. So basically, while trying to calculate M3, you get M4 as your plain text block. And if you consider the scenario further on, you will see that you get Mi plus 1 as your Mi ith plain text block. So one block is dropped completely. You cannot get back the actual block M2 here, or we can say that if the block Ci, ciphertext block Ci is dropped, then you cannot get back the plain text block Mi. Also, plain text block Mi plus 1 will be erroneous. And after that, Mi plus 2 will be actually Mi plus 3 and so on. So one block shift of the plain text will happen in the decrypted sequence of your plain text, right? Like this, M1, then this will be some erroneous plain text, and after that you will continue to get M4, M5 and so on as your plain text blocks. This is the case of CBC. And now considering the scenario of OAP mode, in OAP you basically perform the XOR with the message block with the output of PRF. So the initialization vector IV is first provided as input to FK, and you get the PRF output Y1, and with Y1 you XOR your message block M1 and you get C1. And all this value Y1, Y2, Y3 and so on can be recomputed in case of OAP mode. Now, In case of WebP mode, if some ciphertext CI is lost, say C2 in our example, then again M1 is not affected, of course, because C1 is correct, Y1 is correct, so M1 is correct. But when you try to compute M2, you actually get C3 in place of C2. So you perform C3 XORed with Y2. If you would have done C2 XORed with Y2, you could have got M2 correctly, but as you have got C3 in place of C2, you are performing C3 XORed with Y2, which will give you wrong output. And in the next case also, in place of C3, you have got C4. So you are trying to XOR actually C4 with Y3, which will never give you back M3. So all the subsequent decrypted plain text value will be wrong in case one block. So if your block CI, ciphertext block CI is dropped, you get first I minus 1 message blocks correctly, but after that mi plus 1 and so on all will be wrong. Whatever you get as computation of decryption algorithm, all the plain text you get are actually wrong. Okay. And also for CTR mode is nothing but the counter mode of WebP. Here basically in the first block the input vector is IV, and then the second block it will be IV plus 1, IV plus 2, and so on. So it is very similar to the OFP mode, and you can easily see yourself that the scenario will be similar to OFP mode in case of CTR mode. So that is for ciphertext block CI is dropped, then first I minus 1 message blocks are correctly decrypted, but after that all the computation will be erroneous because all the ciphertext blocks are shifted by 1 bit, so you get all the plain text as wrong. Okay. Proceeding to the next problem. Which of the following is or are false about modes of operation? First option is given at a sequence of n messages can be encrypted using block cipher by making less than n calls to a secure PRF. So, of course, in case of n messages, you have to call at least n number of block cipher FK to get n number of ciphertext block. Right? Next statement is ciphertext computation is parallelizable in CTR mode. Yes, it is, because for the main reason from converting WebP mode to CTR mode is that in case of WebP mode, the calculation of this Y1, Y2 value were sequential. You cannot compute Y2 unless you have computed Y1. If you remember the previous picture in case of WebP mode. So all these are dependent. Y2 is dependent on Y1, Y3 is dependent on Y2. So this computation is sequential. So if you have replaced this way, all the individual input to the blocks with IV plus 1, IV plus 2, and so on. So they can be computed independent of each other, and so that can be parallelized. So that is true statement. Then plain text of any length can be encrypted in WebP mode. Yes, that is true. Any length of plain text, as you can see here, that whatever be the value of any yi, which are maybe pre-computed value. So whatever be your last block of message, whatever number of bits are there present, you just take that many number of bits from corresponding yi and can output. Stateful variant of counter mode is secure, whereas that of WebP mode is insecure. This is wrong. So because we know that stateful variant of CVC mode is actually not secure, but both WebP mode and counter mode as the use. Okay, so let's just analyze the scenario. In case of CBC mode, if you use stateful variant, that is for some session, if you have provided plain text block M1 and M2, and then in next session when you start providing plain text block M3, M4, and you use the previously computed C2 as the IP for next session, that is called stateful CBC mode. And in that case, we claim that it is not secure. Why? So let's show CPA attack in this scenario. So CPA attack means you are you can get some. So in our CPA attack, we will first see the challenge phase. So there is no pre-challenge query phase. We will directly see the challenge phase, and then we will see post-challenge query phase. And how that works is that, let's say in the challenge phase, the attacker gives the challenge plain text M10, M20, and M11, M21. That means this is one value of M1, M2 plain text block, and this is another value of M1, M2 of plain text block. Okay. And then in response, it says the challenge ciphertext IB C1 and C2. That is the format of your ciphertext. Right. Now, this is basically encryption of either this or this one. We need to distinguish that whether it is ciphertext of this or ciphertext of this. So in the post-challenge query phase, what the attacker can do is that it can query the encryption oracle with plain text block some M3, M4 such that M3 is C2 XORed with IV XORed with M10. IV it can see from the challenge ciphertext, and then it also has the knowledge of M10. So like that, if it has constructed the plain text block M3, what happens is that how C3 will be calculated? C3 will be calculated as FK of C2 XORed with M3. Now you replace M3 with this expression C2 XORed IV XORed M10. It gives back IV XORed with M10. So FK of IV XORed with M10 will be exactly same as C1, only if this M1 was actually M10. If it is not, then certainly M11 was provided here in this block. So this is with probability 1, basically the attacker can say the challenge ciphertext is of this particular plain text or this particular plain text. So CPA security does not hold here clearly. And in case of output feedback mode, it is secured in the stateful scenario also, because if you are directly using this Y2 in the next session for encryption of M3 and M4, basically this sequence Y1, Y2, Y3, Y4 is independent of plain text blocks. So you just XOR the plain text block M1, M2, and so on with this pseudo-random strings Y1, Y2, Y3, Y4, and so on. So by no means post-challenge input query can be made to affect the input to ERN blocks. So that's how this OFP mode is in its stateful variant is still CPA secure. And so that was the last option. Okay. Proceeding to the next question. Consider the stateless variant of CBC mode of encryption with a block cipher having 256-bit key and 128-bit block length to encrypt a 512-bit message. Now you are given length of the resulting ciphertext in bits. So if you see the CBC mode of encryption, you basically have to put your plain text length a multiple of your block length, right? So if your block length is 128-bit, your message also has to be a multiple of 128-bit. If it is not, then you add some padding bits, right? And how many number of padding bit can be added? So ideally it should have been like if it is already a multiple of 128 in this case block length, then you may not need to add any padding bit. So you think that okay, now I need zero number of padding bit, and you may face a scenario where your message is just one bit less than some multiple of your block length. Then you just add one more padding bit to complete the uh, message length as multiple of block length. But it can lead to ambiguity in case of the required number of padding bit is zero, or so basically what you pad, the value you pad is actually the total length of your message in byte. Okay, so if we see this scenario here, actually you have exactly 4 plain text blocks available, but you need to add actually one more a complete block to the message, so that no ambiguity arises. And in this additional block, the value of each byte will actually contain the size of your whole plain text message. Okay, so you will basically have total 5 plain text block, and last block having size of 128 bits, that is the block length, or 16 byte, and each of these byte will store the value 16. Okay, that means the number of padded byte is 16, because the whole block is the padded block. So the value 16 will tell the decryptor that okay, the last block you continue cutting down or removing the last padded bytes, whichever has the value of 16. So like that, the ambiguity is not there. So anyway, so our question was what will be the length of the resulting ciphertext in bits? That is, the number of ciphertext block will also be 5, and as you know, the CBC is nothing but length preserving pseudo-random function, or basically PRP is used. So ciphertext length will be exactly same as message length. So we have ciphertext in bit, so 5 into 120, that is 640 bits ciphertext. Proceeding to the next problem, which of the following is or are true about Fistel and SPN networks? First statement is given as SPRP can be constructed using 4-round Fistel network, which you already know is it is true. That is already discussed in the lecture posted. So using Fistel network for 4 rounds, you can get strong PRP. Diffusion is used to produce avalanche effect in an SPN. Okay, that is true, because avalanche effect, as you know, is that difference of even just one bit in the input to SPN network should actually affect all the output bits of the SPN network. That is the objective of avalanche effect, and diffusion helps in doing that. Next statement is S boxes are used to produce confusion in an SPN, which is not true, because confusion is created in an SPN by zoring the input with round key. So that actually prevents the input to directly getting fed to S boxes. So confusion is caused by the zoring of round key. First two options are only correct options. Proceeding to the next problem. Given Fk is a secure PRF, you construct some Fk dash such that Fk dash is equal to Fx if x is even, and if x is odd, you output f of x plus 1. Then the question is, which of the following is or are false? If K dash is a secured PRF, if K dash is a secured PRP, if K dash is a secured strong PRP, and if K dash can be used to instantiate the CTR mode of block cipher. So let's analyze this PRF. So as you can see, adversary can construct such input to the verifier where let's say adversary queries with input x1, which is n minus 1 number of bit of 1 concatenated with 1 last 0. So if x1 is of this form, what happens is that x1 is then even. So if verifier is actually using PRF to output the response to the queries, then y1 will be of the form fk of x1. And next, A, the adversary A queries with x2 such that x2 is of the form 1 to the power n minus 2, 0, 1. This is an odd binary string. So if verifier is actually using a PRF to give the responses to the queries, then it will actually give back fk of x2 plus 1, and x2 plus 1 is nothing but same as x1, right? You add 1 to this string, you get this string back. So this is fk of x1. So basically, what adversary then do is that it checks if y1 is equal to y2. If it is, then it concludes that, okay, I am interacting with a PRF. Otherwise, it concludes that b dash is 1, that is, I am interacting with a truly random function. Now, analyzing the scenario, if b equal to 0, if verifier actually chose the PRF to output the responses to query inputs, then of course always y1 will be equal to y2 according to the definition of fk dash. So that probability is 1. And what is the probability that b was actually chosen as 1? That is, verifier chose to output yi to the corresponding query inputs using truly random function, but yet a got y1 equal to y2. That probability is clearly 1 by 2 to the power n. So the distinguishing advantage of this adversary is 1 minus 1 by 2 to the power n, which is not negligible. And thus we conclude that fk dash is not a secure PRF. And as fk dash is not a secure PRF, so similarly we can say that fk dash is of course not a secure PRP, neither strong PRP, and as it is not a secure PRF, so it can not be used as CTR block cipher. Okay. Proceeding to the next question. Let F is a secure PRF which takes as input of key of length n, and its input x is also of length n, and output is also length n. So it is a length preserving PRF. Then you are given 4 different constructs, proposed construction of PRF, and you have to say whether they are secure or not. So let us analyze one after another. F dash is its key is of length n, and input is of length 2n, and output is again of length n. And its construction is given as fk dash x concatenated with y equal to fk of x XORed with fk of y. So the input to fk dash is basically divided into 2 equal half, and then its value is computed as fk of the first half of input, that is x, which is XORed with fk of second half of the input, which is y. So whether it is a strong secure PRF or not. So this is intuitively should not be a secure PRF, and for counter example we say that the adversary can provide as input of this form, x concatenated with x. So both the halves of the input query can be equal. And in that case, what happens is that this verifier, if chose to reply with a PRF output, then it will compute fk of x joined with fk of x, which is all zero string. So string of length n with all zeros. So adversary will simply check if whatever it gets to see is the output. If it is all zeros, then it returns b dash equal to 0. That is saying that I am interacting with a PRF. And if it is not the case, z is not all 0, then it says that b dash is 1. That is, I am interacting with a truly random function. And now, provided the scenario was actually b equal to 0, that is, verifier decided to communicate using a PRF, then always z is bounded to be all 0 string. And so adversary will return b dash equal to 0. So this probability, the probability b dash equal to 0 over b equal to 0, that is always going to be 1. But what if verifier actually decided to use TRF to give response to the query inputs, but the adversary got to see z to be all 0 string of length n, that probability is 1 by 2 to the power n. So the distinguishing advantage is 1 minus 1 by 2 to the power n. Thus, we conclude, which is not negligible, so we conclude that this construction of fk dash is not a secure PRF. Proceeding to the next example. Here is another construction f dash with key length n, input length 2n, and output length 2n. And fk dash x concatenated y is defined as fk of x concatenated with fk of y. So here also, as you can see, that the adversary can choose to form the input string in as x concatenated with x. Again, the first half of the input and second half of the input are same. Then, if verifier decided to use PRF to give the output, give the response to these input queries, then basically it will be fk of x concatenated with f of x. So both the half of the output string will be equal. And using this property, the adversary can easily distinguish between the output of PRF from output of TRF with non-negligible probability. What adversary does is that whatever it gets to see as the output z, it parses that into equal length, like two halves of equal length, and it checks if the first half is exactly equal to second half. If it is, then it concludes that it is interacting with the PRF, that is b dash equal to 0 is returned. Otherwise, it says it is interacting with the TRF and b dash equal to 1 is returned. And the probability that b dash is returned at 0, provided b was actually 0, is of course 1. And the probability that b dash is returned as 0 when b was actually 1, that is verifier actually was using truly random function to output set, then the probability that in an output 2n length string, the first half is exactly equal to second half, that probability is the denominator being 2 to the power 2n, the all possible strings of length 2n, and the numerator being 2 to the power n, because the first half is exactly equal to second half, and that gives us 1 by 2 to the power n. Distinguishing advantage being 1 minus 1 by 2 to the power n, which is not negligible, and we conclude that this construction fk dash is not secure, although f is a secure. The third option, here f dash is constructed as p length is n, input length is 2n, and the output length is n. Fk dash x concatenated with y is defined as fkx ANDed with fk of y. Now, this symbol is AND, okay, logical AND operator. Now, clearly by intuition, you can say that even though f is a secure PRF, that is individually fkx is a pseudo-random string and fky is also a pseudo-random string, but when you AND them bit by bit, any if you observe the AND table with 3 by 4 probability, you get the AND output to be 0, right? So this is clearly distinguishable from a pseudo-random, from a truly random case. So ANDing two pseudo-random bits output 0 with probability 3 by 4, which is clearly distinguishable from a randomly generated bit where the probability of a bit being 0 is exactly half. So by checking a particular bit of the output for a polynomial number of times, we'll gradually reveal the nature of the generation of that bit. If you see that the probability of some particular bit in the output of being 0 is more than half, then you conclude that you are actually interacting with a PRF. Otherwise, you conclude that you are interacting with a truly random bit generator. So this is also not a secure PRF because ANDing two random string will output 0 in bit, some particular large probability. Now, the last option, again, n-bit key n-bit input and 2 n-bit output, defined as fk dash x equal to fk of x concatenated with fk of x XORed with 1 to the power n. So basically, x XORed with 1 to the power n is nothing but x bar, one's complement of x. So the construction becomes fk dash x equal to fkx concatenated with fkx bar. And this we have already seen previously that this is not a secure PRF. Very simply, you just query the verifier first with input x, then with input x bar. And in both the cases, you first you get fk of x concatenated with fk of x bar, and in the next case you get fk of x bar concatenated with fkx. And by comparing that whether the first half of the first string is equal to the last half of second half of the second string, and the second half of the first string is equal to first part of the second string. If that condition is satisfied, the adversary concludes that it is interacting with a PRF. Otherwise, it concludes that interacting with a truly random function. And this is clearly has a non-negligible distinguishing advantage. And so we conclude that fk dash is also not a secure PRF. So all the four options that were given in these questions are turned out to be not a secure PRF. Pseudo-random property is not satisfied. Proceeding to the next question, let f be a pseudo-random permutation. Consider the mode of operation in which a uniform value CTR, which is n-bit random string, is chosen, and the ith ciphertext block Ci is computed as Ci equal to fk of CTR plus I plus mi. We have to show that this scheme does not have indistinguishable encryption in presence of an eavesdropper. So this is how the ciphertext block is defined: fk of CTR plus I plus mi. We have to show that in presence of an eavesdropper, you are able to distinguish the scenario, whether it is a some particular challenge ciphertext is encryption of M0 or encryption of M1. What you can do is that you can provide M0 and M1 to be of the form where M0 is of the form first block being the encoding of value 1 and second block being the encoding of value 0. So there are two message blocks in M0, and in M1 also there are two message blocks. First block is encoding of value 0 and second block is encoding of value 1. Now whenever the whenever B is chosen to be 0, then what happens is that CB, so the output challenge ciphertext becomes CTR, comma, as if you remember how the computation of ciphertext in case of block cipher happens. So the first counter is output CTR, then CTR plus encoding of 0 is added, that is the I. So in the first block I is 0, so we add encoding of 0 here, and then mi is added. Mi is nothing but the value of first block of m0, which is encoding of 1. And the last part for the second block, the output is fk ctr plus count. The I value is now 1, so encoding of value 1, and the value of mi, that is the next block of the message m0, that is encoding of 0. So basically these two values, fk of ctr plus encoding of 0 plus encoding of 1, they are same. So whatever you see in the ciphertext, its second and third block of the ciphertext will exactly be the same if B is chosen to be 0. M0 is of this form. And if B is 1, that is M1 is getting encrypted, then you will have this kind of form. If K of CTR plus 0, I is 0 for the first message, and first block of M1 is 0, so encoding of 0. And in the second case, I is incremented to 1, so encoding of 1, and the second part of message M1 is 1. So they are certainly not same. So CTR comma some C dash comma C double dash will be output. So by observing this pattern of ciphertext, you can easily distinguish that whenever it gets the part of the ciphertext, the second part exactly equal to the third part, then it concludes that it is seeing encryption of M0, otherwise it is seeing encryption of M1. And that will happen with non-negligible distinguishing probability, because if B is 0, then B dash will obviously be 0, which is the probability 1, and if B dash is 0, if B is 1, so M1 is getting encrypted, then the probability that A wrongly thinks that it is saying encryption of M0, that will happen with negligible probability, because for that these two values has to be the same. Encoding of 0 plus encoding of 0 should be equal to encoding of 1 plus encoding of 1. So that depends on the encoding scheme, and that probability is anyway getting to be negligible. So the distinguishing advantage for A between the ciphertext of M0 and ciphertext of M1 is non-negligible. So such encryption scheme is not secure in presence of its strong. Proceeding to the next problem. Consider a stateful variant of CBC mode encryption where the sender simply increments the initialization vector by 1 each time a message is encrypted, rather than choosing IV at random in each time. You have already seen that in case of stateful CBC mode, where in every session, instead of choosing random IV, if you use the previous CI output as the IP of the next session, then it is not secure, CPA secure. And the reason also we have already seen. And in the similar way, actually, we can argue that in this case also, where for each session the IP is incremented by 1, then the resulting scheme will not be CPA secure. How? So let's say the first session the plaintext was M1 and M2. So let's say assume the challenge phase where the adversary knows the possible values of plain text. It can either be M10, M20, or it can be M11, M21. And it is seeing the challenge ciphertext, which is of the form IV, C1, C2. And you need to determine that whether this challenge ciphertext is an encryption of this or encryption of this. Now, in the post-challenge query case, it can simply query with plain text M3, M4, where the first block of message M3 has this structure, which is IB plus 1. As you can, the adversary can already see the value of IB from challenge ciphertext. It can compute IB plus 1, XORed with IB, XORed with M10. This value is also known to the adversary. Now, what will be the C3 then? C3 will be FK of IB plus 1, XORed with M3 by this formula. And you replace M3 with this IB plus 1, XORed IB, XORed with M10, and you get IB plus M10. This is very similar to this stateful CBC design scheme, where by providing providing query input plain text of this form, you can distinguish that whenever you see C3 is exactly equal to C1, you conclude that M1 was actually of the form M10. Otherwise, M1 was of the form M11. So like that, you can easily distinguish between the scenarios. Okay, so this will not be a secure modified CBC, CPA secure modified CBC. It's not. Proceeding to the next question. What is the effect of a single bit error in the ciphertext when using the CBC, OAP, or CTR modes of operation? Previously, we have seen what happens if one ciphertext block is completely dropped from the output, from the ciphertext block sequence. And now the question is, if from some particular ciphertext block, one bit is erroneous bit, so maybe one bit is flipped, then what happens? Let's first the scenario of CBC mode. So here, let's say some ith ciphertext block CI is corrupted, and in place of CI, we got CI dash, such that the Hamming distance between CI and CI dash is just 1 bit. So only 1 bit got flipped from CI and we got CI dash. Now, whenever we try to get back MI, what we perform is that FK inverse of CI dash, and then we will XOR that with CI minus 1, which is completely okay. CI minus 1 is not erroneous, but the point is FK inverse of CI dash will not be equal to FK inverse of CI. In fact, they will not anyway be related. Although CI and CI dash differ by just 1 bit, FK inverse of CI dash and FK inverse of CI will not anyway related to each other. So we cannot get back MI, of course. Now also notice that the next plain text block will also be affected due to this error in block CI. How? Because whenever you try to, although you receive CI plus 1 completely correctly, you inverse FK inverse of CI plus 1, you get MI plus 1 XORed with CI. Now this CI is corrupted. So basically you XOR CI dash, and it will get you MI plus 1 dash, which is differing by 1 bit from original MI plus 1. So basically 2 plain text block will be affected in case of CBC mode. If ith ciphertext block is affected by 1 bit, then the computation of plain text block MI will be completely wrong, but the computation of MI plus 1 will be same as original MI plus 1 except for 1 bit position wherever the error occurred. Okay. In case of OAP mode, so here let's say for some CI, you receive erroneous block, ciphertext block CI dash, which differs from CI by only 1 bit. So Actually, to get back the plain text mi, you do ci XORed with yi. So this output we are calling yi. Now, as ci dash differs from ci by only one bit, mi dash will also differ from mi by 1 bit position, and rest of the recovered plain text blocks are actually correct. So in case of WebB mode, just the corresponding to the ciphertext block ci, the decrypted message block mi will be differing from original plain text block mi by only 1 bit. But there is one catch here. So the ciphertext block includes IV also as C0, right, in case of WebB mode. So IV, if the error occurs in IV, 1 bit error, then actually all the calculation of y1, y2, or yi, all of them will be affected because they all are related to each other. So then all the calculations of mi will be wrong if the error occurs in IV. And apart from that, any other ciphertext block, if it is affected, then only 1 bit will be affected by the corresponding mi only, corresponding plain text block. Otherwise, it is rest of the blocks will be okay. So that is all for today. As there are very few participants, I guess I can stop here, and thank you for attending.